morning, friends. We have been discussing at length on wing, the different types of strecks which are relevant for our aircraft. And you might have seen by now one lecture by our chief engineer where he has demonstrated you various parts of the airplane. This was done to familiarize you on what are those aerodynamic surfaces you need to be careful as you progress in designing the first conceptual aircraft. And if you recall, we started with a mission requirement, what we said, takeoff, climb, cruise, then loiter, and then landing. All right? We also are familiar with these two diagrams. One is this. This is thrust, drag, lift, weight. We're also familiar with diagram like this. So this diagram reminds you about cruise, and this one climb. And we can also recall we have done something on maneuvering flight where we draw the schematic as this. This is thrust, this is drag, this is lift, and this is weight, and this is radius of turn. If you see these three diagrams, the moment I try to focus here, I write thrust equal to drag, lift equal to weight. And when I focus here, I write T minus D minus W sine gamma equal to M dV by dt. That is net force causing acceleration. And here when I see, the important thing is if I want a particular radius of turn, I need to generate a lift which is n times weight. So this gentleman has to be more than weight so that it can go in a vertical loop. These are the primary maneuvers based on we will be actually configuring our airplane. In this diagram you could see the thrust plays an important role. So as a designer, I need to ask question, how much thrust do I require for a particular airplane? If I try to answer that from this mission, the cruise mission, my answer will be I should have sufficient thrust which should be able to balance drag, and that is half rho v square s into CD naught plus k CL square. When I see here lift equal to weight, it tells me I need to have that much of thrust which should give me enough velocity. If I see this equation, then it tells me I should have enough thrust which should give me enough speed so that for a given CL, I should be able to produce adequate lift to balance the weight. That is how thrust get connected here as well. Because you understand, if I want to give speed, it will also cause drag. So thrust should be good enough to handle this. And if I come here, I know that thrust should be enough to give me this right hand side balanced for unaccelerated flight. If it is an accelerated flight, then thrust should be d plus w sine gamma plus m or w by g into whatever acceleration you want along. If I come here, it says I should have enough v such that for a given CL, lift should be equal to n times w. N could be 2, 3, 1.5, 4. So here also you could see thrust is implicitly present. So that is where you could see thrust is extremely important, and hence for designing an aircraft, we should also make a judicious choice of what is the thrust requirement. When I talk about thrust, please understand the aircraft primarily will be covering having two types of engine. One is jet engine, another is propeller driven IC engine. So whenever you are talking about propeller driven engine, we try to rate the engine in terms of power. And jet engine, we try to rate them in terms of thrust. So this distinction should be in our mind. Okay? Now come here. This part, you know, this is warm up plus takeoff. And explicitly what we understand, that the airplane starts with V equal to 0 and thrust is applied on the aircraft. If the aircraft, here is the thrust, here is the thrust, opposing is drag, some lift will be there, and then there is a friction force. Okay? And of course, because there is a weight, and you can draw a reaction which gets coupled with friction force. What is important here is that the airplane initially is at V equal to 0, right? And there is a particular speed V liftoff, which you know it is 1.2 to 1.3 times V stall. Meaning is this, if the aircraft attains this V liftoff speed, then the airplane will start taking off, right? It goes like this, takes off. That means from V equal to 0 to V equal to liftoff, this responsibility comes from thrust primarily. This is thrust job. So it has to accelerate the airplane from V equal to 0 to a speed V equal to liftoff. Now, if I write V liftoff is equal to 1.3 times V stall, you will find between 1.2 and 1.3 times V stall is V liftoff based on different aviation regulations. So it doesn't matter for our understanding whether it's 1.3 or 1.2. The main point is V liftoff is if 1.3 times V stall, that means 1.3 times under root W by S to W by S by rho CL max. Now if you want V liftoff to be smaller, if I want V liftoff to be smaller, then options are W by S should go down, CL max should go up for a given air density. Right? So let us say how much will be V liftoff will be primarily decided by what type of aerofoil you have chosen, which is having CL max, whether there is a flaps or not, we will come to those things. And what sort of a wing loading? Wing loading low means large wing area. If there is large wing area relatively, then takeoff speed will be less, but same time drag also will increase. It will become more sensitive to wind. So all those issues we will be covering in the discussion of W/S. And flaps, high lift devices, will cover on CLmax. Today what we are trying to understand, once we agree from V equal to 0 to V equal to liftoff, I need to achieve, then also implicitly we say that I need to accelerate this airplane from V equal to 0 to V liftoff as early as possible so that this distance is less. That means I have shorter takeoff distance. We cannot expect that aircraft will take a large takeoff distance beyond other than which is otherwise not possible. General tendency will be you try to design an airplane so that its short takeoff distance or takeoff distance is not that large. So what is the message? Message is, one is you try to see that V liftoff is low. That is taken care by these gentlemen, W/S and CLmax. But once V liftoff is fixed, then I want this distance should be as low as possible, as far as possible. So it needs to have larger acceleration. So larger acceleration means T/W should be high. This is important. If T/W is high or higher, then it will have a shorter distance for takeoff. So T/W plays an important role in deciding, in affecting the takeoff distance. This is one. Now come to climb. Let us see what is the issue in climb. In climb, you know that T minus D minus W sine gamma equal to 0 if it is climbing without any acceleration, like a rectangular path, it is going with a constant speed. So here you see T/W is equal to W gets cancelled to sine gamma plus D/W, which roughly I can write as sine gamma plus 1 by L/D. I am assuming lift is equal to weight, the gamma being small. So what is the message? Message is how much T/W you require will be decided by what is the climb angle you want. Right? Typically, transport airplane, you will find T/W as 0.2 to 0.25. This is a number, is okay. But if you are designing an aerobatic, which can go like this, can hold the airplane and do a lot of accelerated maneuver, then you will find T/W maybe 1 or greater than 1. This is fine. So then I write T/W as a role in climb. So if you want climb rate to be higher, if you want climb angle to be higher, this T/W is a design parameter you need to have. But somebody may ask me a question, when I am writing T/W, that means am I only talking about jet engine? What about propeller driven IC backup engine or prop engines? So their answer is simple, nothing new we require, and you are familiar with this. We multiply both sides by V, so we get T minus dV is equal to W V sine gamma And here you find that sine gamma, V sine gamma, which is nothing but rate of climb, is given as TV minus dV by W. And TV is nothing but what? Power available. So power available minus power required by W, which I can write power available from the engine by W minus power required by W. So this man, power available by W, is somehow closely related to power loading. So PA V available by W is actually, by definition, is inverse of power available by W is basically inverse of power loading which is given by W by horsepower, that is the power available. So T by W was thrust loading and W by horsepower available is power load. It is a matter of definition. So when we talk about propeller driven engine, we try to talk in terms of power loading. When we are talking about jet engine, we talk about thrust loading. But at the same time, you will see that this power loading can be interpreted through thrust loading as well. We will discuss that, right? Okay, so this part I am stopping here. Now we are coming here to call cruise. Cruise, you know, thrust equal to drag, lift equal to weight. So thrust by W is 1 by CL by CD. So for T by W cruise will be decided by what is the CL by CD cruise. And this is important. You must understand as a designer what is the meaning of this. If I write T by W equal to 1 by CL by CD, and let's say this is CL by CD cruise, and if you want to fly at optimal condition, then CL by CD may be maximum, but not always possible to fly at CL by CD maximum. But important point is, if you plot CL by CD versus V, you will find you need to have a definite value of V to have CL by CD desired, right? That means your thrust loading should be enough to balance that. That is why we call it thrust matching. That's why if you see in textbook, when they're trying to find like this, they give a title called thrust matching. What is the meaning of that? If I want to fly at CL by CD cruise, then T by W is 1 by CL by CD. I have to ensure that T by W for cruise is exactly given by this. Then I will be able to maintain. We have been talking about T by W for cruise, for takeoff, for climb, but also you understand the moment we talk about thrust or power for that matter, we also ask a question, will this airplane be able to achieve the speed maximum? Assuming that at that speed, at that dynamic pressure, the structure will be good enough to withstand the load. That is the assumption. Because you cannot go on increasing the speed or the dynamic pressure. Why I am saying dynamic pressure? At sea level, you may be able to fly the machine at 300 meters per second. But as you go higher and higher, if you want to fly at 300 meters per second, the structural load will reduce because density is reducing. But the reverse, if you are flying at 300 meters per second at 10 kilometers, and if you want to fly at 300 meters per second at sea level, even if your engine gives you power, you have to ensure that now the dynamic pressure has increased, whether the structure will be able to withstand that load or not. So what I am saying, assuming that structure is good enough to withstand a design Vmax, the question is, for Vmax, whether my thrust is sufficient or not, or the power is sufficient or not, right? With this background, I can write T by W and W by S. They play their important individual role, and also they decide the final design together. Okay? And you will see why I am saying that. If I am talking about for short takeoff distance, I need W by S to be low, and next T by W should be high. Now, if you want T by W to be high, that means thrust generated is higher. So what happens for a given technology, it is expected that the engine size will increase, the weight also will increase. So it may affect your takeoff weight. So all this conflict will come. W by S low means S is very large. It may add up to the weight. Okay? So it is, finally you will see that we have to do a lot of compromise, but standalone we should know these things. Also we have understood aircraft with high T by W will help in accelerating fast, number 2, climb more rapidly, number 3, reach higher maximum speed and sustain higher turn rates. So obviously, if you want to turn, you have to bank, and when you are banking and turning, the moment you bank, it will lose the height. So you have to increase the speed, because you may not be able to increase the angle of attack. It may touch the stall. You have to increase the speed, so you should have enough thrust available, right? So this is advantage. The loose disadvantages are large engine. If you want T by W higher, more fuel generally, and takeoff weight may increase. Why I am discussing this, that you should understand, finally we have to do lots of compromise, balancing act, some advantage, disadvantages, they may be conflicting. Not only T by W, it may come from wing loading. So as a designer, chief designer has to look every parameter and see what is his goal, and he tries to find out that path which gives him what is desired. There is another point which is very, very important you people should realize. Before you go to anything in detail, when I am talking about T by W, right, and if I write takeoff, what care I must take? If I talk about thrust, you should realize that thrust, what you are talking about, static thrust, their availability with altitude will drop. If you take a jet engine or a propeller driven engine, IC driven engine, you'll find as the altitude increases, the density of air reduces. So your thrust available goes down. When you're talking about static thrust, which is generally rated at sea level condition, and if you are talking about thrust at cruise, you must ensure that what is the altitude at cruise? Say rho cruise. So I must correct this to the altitude of operation. That is extremely important. Okay? This is altitude effect. Similar thing is true for power from a propeller driven as well. Directly proportional to the density. As density reduces, thrust available, power available also reduces, and mostly it is not a bad approximation, rho at altitude by rho sea level. If you multiply with this factor, the thrust static or power static, you will get the value of that at that altitude. This is general guideline. Now, think of a propeller driven engine. Its thrust also reduces with V speed. In fact, if you write this is V by Nd, if you see the propeller driven engine, the advance ratio. So what is the RPM, what is the diameter of the propeller, what is the speed? In general, you can say the thrust available from propeller driven engine, the dynamic thrust drops. It's always less than the static thrust. So I need to know what is the dynamic thrust available during the operation. That is, if I am talking about cruise and moving with some speed, if I talk about T by W here, the T should be the dynamic thrust. Dynamic thrust plus the altitude effect taken here. Right? This is extremely important. Typically, power available for a propeller-driven engine, they remain almost constant with speed. Of course, for a propeller, you have to ensure that the tip speed condition is met. For the jet engine, this is propeller. For a jet engine, it is roughly, you can say, thrust remain constant with V. So dynamic thrust corrections, if you are doing for a jet engine, you can assume that, okay, it's not going to change with the speed, and power is almost remaining constant with speed. This is the initial design assumption you must have, which is not very bad assumption. This is fairly okay. But do not forget, the altitude effects are predominant. It goes with the ratio of density at altitude by the density at sea level. These two things you should keep back of your mind. So whatever T by W during operation we are talking about, we should talk about dynamic thrust corrected for altitude effect. Dynamic power corrected for altitude effect. Right? That should be back of your mind. Some statistical data may be useful, and every time I am telling you, please refer some book on aircraft design, whether it is Raymer, whether it is Torenbeek, whether it is Google Uncle, whatever it is. This sort of data gets updated, and you must use those. T by W naught, W naught is takeoff weight, versus max, M max, it is Mach number. This table is useful. For jet trainer, jet fighter, this is like dogfight, then jet fighter otherwise, and jet transport. T by W is calibrated as A m max to the power C, and you will get the values of A and C from this table. For jet trainer it is 0.488 and C is 0.728. This is for dogfight, it is 0.648 and this is 0.594. This is 0.514, 0.141, 0.267 and 0.363. These are typical guideline numbers. And I again and again request you, please use latest data sheet so that a lot of new ingenious calibrations are given to make the designers handy. We are talking about thrust matching. That is T equal to T by W equal to 1 by L by D equal to 1 by CL by CD. And you know, if it is a propeller driven engine, if you want to go for R max, then the condition was it has to fly such that L by D is maximum. So that is CL by CD should be maximum. So you put that number here for if your mission is getting a maximum range with the propeller driven engine, that this will give you what is the T by W cruise requirement. And you have to ensure that really this T by W cruise available at that altitude, because you know whatever static thrust at ground available, that is going to reduce at that altitude. You also know the weight of the airplane at the takeoff is going to reduce at that altitude. So you have to give appropriate corrections and ensure that T by W, not takeoff, is such that you at cruise you get this value. This is important. You would design your airplane in such a way that T by W at takeoff is such that when it goes for a cruise to an altitude, T by W cruise is given by 1 by CL by CD, and CL by CD given by CL CD maximum for range maximum for a propeller driven airplane, and similar for a jet aircraft. You know that CL by CD, it has to fly for range maximum is 0.866 L by D max, or 0.866 CL by CD maximum, depending upon what type of airplane you are flying or designing. The requirement for T by W cruise should be evaluated like this, and you should design that aircraft T by W not takeoff such that as it goes to that altitude, you know very well thrust is going to reduce. You correct the thrust for altitude, and for dynamic thrust, correct the weight because fuel is going to change, and ensure that this, after doing that, T by W cruise given by 1 by CL by CD is available. That is the designer's job. Okay? We were talking about Vmax. It is important to see now, if I am thinking of Vmax, maximum speed, what are the design parameters they are going to play a role, right? Before I go for power loading. You know, for a cruise, you see, thrust equal to drag, so I can write this half rho V square, this dynamic pressure, S into CD naught plus K, CL square, and K is 1 by pi, aspect ratio E, and CL square here. And also I know CL is W by Q infinity S. So I can write thrust equal to Q infinity S CD naught, mechanical, plus W square by Q infinity S pi E aspect ratio. What I have done is CL replaced by W square by Q infinity square S square, and this Q infinity one gets cancelled, SS gets cancelled, so this is remaining. So I can write Q infinity square S CD naught, if I do like this, minus Q infinity T plus W square by S pi E aspect ratio is equal to 0. And if I assume, solve this for a given Q infinity, T equal to T max, thrust available is maximum, corresponds to V equal to V max, that you know very well in performance course. If I plot thrust versus V, this is thrust required, which is equal to drag for a cruise, and thrust available with V almost remain constant. So this is the point which is V max I'm talking about. That is how it has been developed. If I do this, then I get an expression which is important. V max is equal to T by W max into W by S plus W by S T by W square max minus 4 CD naught by pi aspect ratio E You can refer this expression from Anderson book on Introduction to Flight. So what is this expression telling? That Vmax will increase if T by W max increases. Vmax will increase if W by S increases. Do you see the interesting point? Vmax will increase, T by W increases, naturally it will give more acceleration, but Vmax will increase if W by S increases. That means S is smaller, so drag is less, so it will accelerate fast. Remember, for Vstall, I want W by S to be smaller. If W by S reduces, wing area increases, so Vstall reduces. But if you want a Vmax, then you want W by S to be higher. So that area is less, drag is less, it accelerates. So you could see that Vmax increases. If you want to increase Vmax, you need to increase T by W maximum, W by S, and also reduce the parasite drag coefficient. The next class you will see this term, you yourself can do it. This is linked to L by D maximum. Check yourself, so you'll understand. If I want to synthesize the design, I need not only talk in terms of T by W. I have to look for W by S, I have to look for L by D, I have to look for CD naught, I have to understand what altitude I am going to take off or cruise. All these things, they merge to have a good optimal design. Right? Thank you very much.